Okay, so let's finish going through this, and then with the last session, we'll actually do this, what we'd intended on doing. I just want to make it through this because it not only talks about the rel perm part of it, but it says what's the impact on the performance. Okay, so the papers are trying to address issues related to the modeling and the measurement of relative permeabilities, specifically for simulating gas condensate well deliverability. So one issue that we try to answer is the saturation hysteresis and its effect on KRG. The only thing we know or knew before we looked at the paper is that the flow phenomena in region 1 will always be steady state. But what the paper talks about is that during the life of a well that's been shut in probably hundreds of times during its entire life, started back up at rate increases, rate decreases, that the saturation hysteresis in the near well region, it's both imbibition, drainage, cyclically throughout its entire life. So the question to be answered is, if you have cycles of hysteresis, but then you come back to a steady state flow condition, does the steady state KRG change if you've seen some hysteresis in one direction or the other? So we did laboratory experiments to study that. Okay? Specifically. Of course, if it had an effect, life would get much more complicated. Just like anytime you have hysteresis being important to the rel perm, you have a big problem because there's no really good rel perm models out there that handle hysteresis. So it ends up it didn't have an effect, at least not a significant effect. The second was the capillary number effect that we've been talking about now. The third was whether you could reach velocities that had both an improvement by capillary number effect and a deterioration of KRG because of the conventional high velocity flow effect of Forsheimer. And then how to composite all these effects for real applications of real wells, be it a vertical radial well, a vertical hydraulic fracture well, etc. So that's what we're trying to look at. So we've already gone through this. This is a summary of everything we've talked about during the course. So now the saturation hysteresis effect. So how we're going to study it, we're going to simulate with a fine grid model the normal production history of a well. We're going to have annual shut-ins. Will be simulated during a 5-year depletion period. And then we're going to look at the performance of saturations and so forth prior to the shut-in, during the shut-in, and after the shut-in, how the saturations change prior to, during, and after the shut-in when the well's put back on, to get a feeling for what degree of hysteresis, saturation hysteresis do we see. So this is just the producing GOR. We've got the first year, it's producing the richest fluid here. We shut the well in for half a day, and then we produce it again for the remainder of the year. This is just looking at 1 day before the shut-in, during the shut-in, and 2 days after the shut-in. But in between here, we're producing it continuously. So what you can see is after the almost full year of production, everything is stable coming into the shut-in. During the shut-in, where there's no GOR, and you always see that the GOR starts low after the shut-in. In fact, GORs that are more oil-like than gas-like, and then go back into more or less the same within 2 days of what it was before the shut-in. So it's a short-lived transient, if you will.
Does this transient depend on the permeability?
I'm sure it'll depend somewhat on relative permeability. This is just to kind of map out.
So not the relative permeability, but the absolute permeability of the. Like, was it a very tight formation that you checked?
I think, gosh, that's in the paper, I'm sure.
Okay.
I would suspect we looked at something with maybe 1,000 millidarcy feet. Okay, so this is the initial saturation. Okay, so it's initially gas. You have the initial saturation build up during the first 2 days of production from the well, time 0. Okay, it went below the dew point here, imbibition up here. We shut the well in, we got a drainage. We put the well back on, we get another imbibition here. And then after the next year, we come in with this next to lowest saturation profile here. Actually, it's this one. I'm sorry, the oil saturation in blue up here. That's after 1 year. It's at 55%, 58%. We shut it in. It goes to 100% oil saturation at the well. This is at 2 meters away from the wellbore. So it's 100% oil saturation the first few meters. Remains so during the shut-in, and when you put the well back on, it drains back down. So we get repeated imbibitions and repeated drainages, whereas the first cycle is imbibition, drainage, imbibition. So you see it's all over the map. That was at 2.2 meters from the wellbore. This is at 3.5 meters from the wellbore. This is the saturation profile at the end of the 12-hour shut-in. So the initial shut-in, basically it came in, let's see, at the end of the 12 hours. So it's 100% oil out maybe to 3 meters, 3 feet. And then it has a critical fluid. It's a phase labeling issue. So it's labeling it oil here, gas here. There's actually a two phase region out, 10 feet away from the well. That's from the initial production. At the end of the shut-in for the others, you can see this saturation profile.
The red curve is showing the production, and the rest are the shut-in.
No, these are all at the end of 12-hour shut-in. So for this thick red one, the well's produced for 2 days.
Okay.
And this is after the 2-day shut-in, or the 12-hour shut-in, after 2 days of production. The others, it's been producing for a year.
Okay.
And then it has a half-day shut-in. So measured 3 types of hysteresis on a Berea core in the low permeability North Sea sandstone: velocity hysteresis, drawdown build-up hysteresis, and variable bottom flowing pressure multi-rate type hysteresis. So basically, we are controlling the gas rate. The pressure in the core was also being changed. This is 100 bar. We increased the core pressure. Here we kept the same rate. So we did all sorts of hysteresis on this, and the delta P translates into the KRG. Basically, always coming back when you have the same base rate, you came back basically always to the same KRG, even though you had all these deviations of different types because of rate or pressure changes. So whenever you came back to the same flow rate and pressure, you always got the same. That's within 5%, these points here. So the saturation change in the condensate blockage is neither imbibition or drainage. It's cycles of both. It doesn't matter what we call the saturation hysteresis. It only matters whether the hysteresis has a quantitative effect on KRG. And the measurements indicate only a marginal effect of even very severe saturation hysteresis on this relationship. Effectively no effect at all for rich condensates, and there was a smaller effect on leaner condensates. And probably this has to do with the long transient time to reach new steady state conditions for leaner condensates. Capillary number effect, experimental observation of the capillary number effect, developing the correlation that we talked about, using the model to fit the data and integrating this into pseudopressure model. So this is the equation that we talked about. Some of the data, immiscible, low capillary number type data. These are just different types of models. We were talking about the Cori that drops down much more rapidly than the Karichi and the ARCO model. The box here is basically marking where region 1 will be found from 0.1 to 100 ratio. Here you see the ratio, KRG, KG, KO ratio is basically the same. So you've got huge differences outside the range, but within the range itself, they're essentially all giving the same fundamental relationship. Okay, this is region 2 behavior. This was immiscible to miscible transition function. These are typical capillary numbers for radial well. This is example fit of some of the measurements that were made for a constant KG-KO ratio using different fluid systems. This was the data from that North Sea neurocritical fluid system. And then this inertial or high velocity flow, Forsheimer type extra pressure drop. Recognize the large uncertainty in estimation of the single phase. It's not easy to get the single phase beta term. Effect of the KRG on that beta. I think there was like 3 or 4 different correlations in the literature before we started doing this. And then integration of the 2-phase high velocity flow effect into the pseudopressure model. So yeah, here's those different correlations. Composite blockage effect, the formulation of the pseudopressure, incorporating in a reservoir simulation, and including the 2 into cell-to-cell calculations. And the reason for this is so that you can do your fine gridded single cell models, including the capillary number and beta dependency, to get the right answer, and then compare that with the pseudopressure treatment that includes also capillary number and beta. And then just generally to study the composite effect of all of these on actual well performance. So to capture the velocity dependence, you have to basically get velocity as a function of pressure to include it in the integration of the mobility term. Mobility has to be a function of pressure. So the capillary number velocity is estimated from pressure using, in the case of a radial flow, the radial flow equation. You need this to get the capillary number and the beta term. These are just example gas pore velocities that you can attain in conventional labs, and then these are extended lab velocities that were used in our JIP. Here are capillary or pore velocities seen in a radial model. I'm not sure why we didn't go to lower pressures here, but it's I guess at the well bore would be here. This is the gas relative permeability using the immiscible curves like we've been talking about through the course. If you include the capillary number effect, how much it lifts up potentially the relative permeability, and then how much you can lose again because of the Forsheimer type deterioration. This basically translates this into the total mobility. So you can see how much more pessimistic it is if you don't include the capillary number dependence, at least for radial well, for vertical wells. There's a big effect here. And then again, you lose this from the Forsheimer behavior. So this is an example of the rate time performance using immiscible curves, using capillary corrected curves, and capillary corrected with the high velocity flow. This is for a vertically fractured well. Here you see there's much less effective capillary number because the velocities are lower, but there's still an effect. And then basically main conclusion, saturation, hysteresis, and gas condensate wells consist of endless cycles of imbibition and drainage in the condensate blockage region. One of the reasons this was a big deal is that there was papers even at the same conference, and had been for the last 15 years before the paper, about people arguing, is condensate blockage an imbibition or drainage process? Ragamon or Jones, it was all, there was all sorts of discussions about it, but in reality, this was just to end that discussion, that it's neither, it's both, so get over it. The effect of the saturation hysteresis based on laboratory measurements seems to be small. Capillary number dependence can have a significant impact on reservoir well performance. This is shown both experimentally and in production forecasting. And it indirectly supports this long-standing field observations that condensate blockage is often not as large as predicted using rock relative permeability curves. So people like Fussell in 1973, they made, I think, the comment in their paper that even though they modeled everything correctly, compositional model, radial, fine gridded radial, they captured all the blockage effect, they put in rel perm curves, that the blockage effect was not consistent with the field observations of the well performance. So that's where that comes from. So these were the companies that were supporting that GIP. I don't think there's any of them.
The Res Lab, that's the lab of doing the experiment. Res Lab on the left.
Yeah, Res Lab was the one doing the experimental workout.
Similar to which is now known as stratum.
Yeah, so stratum. So it's now stratum. Salga was bought by Hydro. Hydro was bought by Equinor. Mobil, Exxon. Yeah. Oxy's still around.
But there was some Oxy and Anadarko.
Oxy and Anadarko. I think they bought Anadarko. Yeah.
There was one figure where you showed the KRG versus KRG, KRO. That it's the same for all the different models. At least in the range of interest in the blockage region.
This one?
No. Maybe down. Down.
Yes.
Here. So here,
This was we basically created from 3 different correlations with very different KR saturation functions. We created, but they all had the same KRG versus KGKO, or the same, almost identical. Okay.
Yeah.
And it's just, so basically in the range of interest, any of those models can fit this type of data, but in this area up here, the differences would affect region 2.
Yeah, region 2
is out here.
So the block, like condensate blockage skin, will be the same, but it's the difference comes from.
Yeah.
So if you are just doing, for example, MBEL or like without any reservoir like simulation modeling, then whatever relative permeability curves you will put, you will get the same results. Even if you include the pseudo pressure, because you don't have region 2.
Well, region 1 there's a big influence of which rel term you pick.
On region 1?
Yeah.
Yeah, but region 1 is...
Because, that we picked 3 correlations with certain parameters such that we got the same KRG versus KGKO. If you change the exponents of the different correlations, you can get quite a wide range, like the pore size distribution range of KRGI.
Okay.
I have a question for the plot showing the gas production profile for the radial well case.
A plot from this figure, from this presentation?
Yes, from this presentation.
Okay. Which was it?
At the very end, like where you have the gas production profile for immiscible capillary number and high velocity flow effect for the radial well case.
Yeah.
Here?
Yeah, but for the production over time.
Is it before?
Going down.
Going down? Here. Okay.
Yes, yeah. So here we see that the high velocity flow effect or non-Darcy effect has not a real big impact on the gas production profile.
Mm-hmm.
Despite the slide before or 2 before, we saw that the mobility is significantly decreased if we take into account the non-Darcy flow effect.
Right. Yeah, basically it's basically the area, these 3 different areas are the difference between the green and the red is this area in here. If the high velocity flow, if you ignore it, then it's the green. If you include it, then you have to add, you take away this area here, the green area.
Yes, but here in the mobility plot, it looks more significant, that effect.
It's probably just your eyes. You have to remember, you have to integrate the whole area. So it's the green box relative to the total area. Yeah, I mean, I kind of agree that it doesn't show up as strong an effect.
Maybe because you get some extra.
Yeah, this is at a particular. This is maybe initially this plot here. I don't know. Flowing bottom hole pressure is 3,800.
Yeah, and dew point pressure is 5,500. So it's initial fluid.
Yeah, so it's not a very large drawdown. Flowing bottom hole pressure is pretty high. So I suspect it's maybe even before and the one you're off plateau, the other. So I don't know. It's an illustration. It's kind of a cartoon illustration. It's not. If you looked at it for each time here, then it would definitely look different.
But it's also should
and
depend
maybe a
on
second
the.
question. Yeah,
Go ahead, Rico.
I want to ask how the fracture is modeled in this simulation. How the hydraulic fracture, is it explicitly modeled by small grid blocks with high permeability or?
Yes.
Okay.
Yeah, the hydraulic fracture is gridded. But there's, I think, it's like an infinite conductivity type. Hydraulic fracture conductivity is not an issue. The main effect is that you have much lower flow velocities.
And for hydraulic fracture case, can condensate blockage ever be a severe issue? in a particular case, or as soon as the well is hydraulically fractured and is performed everything all right, it's not a big issue.
Yeah, so it's semantics here. A big issue, what I would say is that the most effective, certainly the most cost-effective, if not the most technically effective way to minimize condensate blockage where it's a problem is hydraulic fracture, hands down. But the blockage problem doesn't go away. So like here, if you had a dry gas, if you had a dry gas non-stimulated well, you probably would get a similar production profile to this hydraulically fractured condensate well. Okay? So what you're doing with hydraulic fracture is you minimize the effect, but you can never get rid of condensate blockage. And you minimize the effect because you have linear flow, so the pressure distribution or the pressure drop per inch is much lower for hydraulic fracture than it is for a vertical well, where you got pressure is proportional with log of radius. So you have the blockage effect, but it doesn't add that many PSI extra pressure drop.
So as the drawdown is decreased, it takes much longer to build up the same condensate saturation or accumulation?
No, I think you get stabilization the same amount of time. The time it takes to build up the region 1. It's just that the KRG reduction will be the same level, okay, because that's independent of flow geometry. It's dependent on the CGR and the flowing bottom hole pressure. So that doesn't change. So the level of KRG is the same for radial and vertically, forgetting the capillary number dependence. The KRG level is the same, but you don't have the big pressure drop right at the wellbore where you have the low perm. The pressure drop in a hydraulically fractured well is distributed more evenly away from the hydraulic fracture. So a bigger part of the reservoir pressure drop is seeing original KRG, region 2, region 3. So it'd be like putting if you had a damage in the first foot versus having a foot of damage 100 feet away from the well. You know, which would you rather have? You'd rather have it away from the well. So by having a vertically fractured well, you linearize the pressure drop outwards away from the wellbore. So you have much less of the pressure drop in the first 10 feet than in a unstimulated well. That's the effect. It's not the time it takes to reach steady state or something.
But I think this assumes an more or less ideal fracture, whereas in reality we see that most part of the fracture is damaged. And there has been a lot of papers now published by consortium, fracture. There's a consortium for hydraulic fracture in the US. And they see that the pressure drop is not really linear within the fracture and is like also taking the shape of due to damage which happens in the hydraulic fracture. It takes a more exponential flow. So the question was why we are asking is that because we were writing a paper about it and we saw that there is actually an effect of condensate blockage in vertical fractures. Because our initial thought was that it also is infinite conductivity, there is no pressure drop within the fracture.
Mm-hmm.
But when we compare it with the real data, we see that the fractures are not really working as their ideal.
Well, I mean, if you put lower permeability in the hydraulic fracture, then clearly, that in itself is, even if it was dry gas, in a sense, you're not getting the full value of your hydraulic fracture, right, compared with infinite conductivity. That's the first thing. On top of that, you're going to introduce a KRG effect in the hydraulic fracture. But that I would use straight line rail perms. Okay, so you're never going to get down in the 0.03, 0.05, 0.1 KRG range within the hydraulic fracture. I'd have a hard time believing that.
Not within the fracture, but on the face orthogonal to the fracture, on the formation which is adjacent to the fracture face. So by reducing the fracture conductivity, you are getting much higher drawdown. This drawdown causing the condensate accumulation on the fracture face. And then if it's fractured face with a matrix is also damaged, which most of the time is happening to fracture fluid leak off, then that's what we saw from the simulation, that you see some effect of condensate.
Okay, but if you say you have a let's say you have let's say that you have a 5 millidarcy rock. In the first foot, it's 1 millidarcy because of this leak off damage, okay?
Yeah.
And then in the hydraulic fracture itself, there's restriction there too. It's okay. So the fact that you have the damage of 1 millidarcy in the first foot just by damage, if you put on top of that the condensate blockage, then of course, yeah, that it's worse than just having blockage. But I'm not sure the KRG is going to be the same if it was the 1 millidarcy or the 5 millidarcy.
Yeah, but the effect is much stronger when it's 1 millidarcy.
Okay, yeah, that could very well be true. That you're yeah, I mean that could very well be true. I mean, if you just make a radial composite model or a hydraulic fracture model or whatever, and you lower the perm in the rock adjacent to the hydraulic fracture, 1 foot, whatever, you're saying that you get much more effect of the blockage in that case than if you have 5 millidarcy everywhere in the rock.
Exactly.
Okay. Yeah. No, I don't think I've ever looked at it. So I'll certainly, I think it's an important issue. If you really believe you have damage in the rock directly adjacent to the hydraulic fracture, then I would try to clean that up some way or another.
We're also trying to.
Yeah.
The paper might be a little bit interesting for you to get your opinion on that.
Yeah. No, I've never looked at it. I don't think we've ever looked at physical damage adjacent to hydraulic fracture with blockage. No. Okay. Well, I look forward to reading the paper. So, but I'm assuming it's damage from well test interpretation above the dew point, things like that.
Well, most of the damage is coming from the fracture fluid leak off.
Yeah.
Because if your formation is not really tight, it's low, moderate permeability reservoir, then there is an excessive fluid leak.
I know, but you must see the permeability, this going from 5 to 1 millidarcy in well test interpretation or something from.
No, we really didn't see it from the well testing, but that was one of our assumptions. and we were trying to match the bottom hole pressure,
Okay.
the measurement. Yeah. So we were trying to manipulate, and we knew that there is an excessive fluid leak-off, and so one of the chances, one of the possibilities was that this can be explained. This high pressure drawdown can be explained by excessive fracture fluid leak-off or clay swelling.
Okay. And when you added that damage permeability near the hydraulic fracture, and
then we saw the effect of
and then you got a better match.
See it.
You got a better match of the performance.
Yeah, more or less.
Okay. Yeah. No, it's interesting. I've never looked at it.